Here is the promised hard problem. Integrate 2x times cosine of x squared. The integrand is already a tree in our symbolic language. We know one answer because the previous episode generated this pair. But the search procedure receives only the integrand. It must discover a candidate without looking at the hidden source. Reversing derivative rules does not create one deterministic evaluator. A cosine might match a direct table entry. A product might suggest integration by parts. A nested function might suggest reverse chain rule. But only if the remaining factor matches the inner derivative. Choices are now part of the computation, so represent strategies, costs, bounds, and outcomes explicitly. The root enqueues 3 declared strategies. Cost 1 tries the direct table and fails because the whole integrand is not a table form. Cost 2 opens reverse chain and finds a possible inner function. Cost 4 probes integration by parts. But that strategy's subgoals are outside this small engine, so the branch is deferred. Cost 5 reaches the reverse chain candidate and sends it to verification. The queue always expands the lowest current cost. Our accepted node receives score 5 for total cost and 2 for trace length. Cost here is an engineering policy, not a theorem about mathematical elegance. We could charge for expression size, risky rules, or expensive subproblems differently. The crucial point is that the ranking policy is visible data, rather than an accident of branch order. Flatten the product into 3 factors, 2x and cosine of x squared. The cosine rule suggests an inner expression, x squared. Everything outside that cosine becomes the proposed differential factor. 2x. Now call the forward differentiator on the inner expression. It returns exactly 2x. The structural match succeeds. Reverse the sine derivative rule. If cosine of an inner expression is multiplied by that inner derivative, propose sine of the inner expression. The candidate is sine of x squared. This is a generated hypothesis, not yet an answer. The indefinite integral also permits an arbitrary additive constant, which we attach after a representative candidate passes verification. The verifier knows nothing about reverse chain search. It receives sine of x squared, applies the sine derivative rule, differentiates x squared, simplifies multiplication by 1, and orders the factors. The result is exactly 2x times cosine of x squared. Structural comparison succeeds, all 4 numerical residuals are 0, and the candidate is accepted. The final family is sine of x squared plus an arbitrary constant. Search supplied one representative, calculus supplies the constant family. Generator and verifier remain different interpreters with different failure modes. A bad search strategy may miss an answer. It cannot make the independent checker accept a derivative that does not match. Now ask the same engine to integrate x times cosine of x. The direct table fails. Reverse chain sees inner x, whose derivative is 1, but the remaining factor is x. So it does not match. The parts probe recognizes a product but cannot expand integration by parts subgoals. The bounded frontier empties. The engine returns unknown. Unknown is not a proof that no antiderivative exists. In fact, x times sine of x plus cosine of x passes our verifier for this integrand. A richer integration by parts strategy could find it. Honest software reports the boundary of its search language and budget. It does not turn failure to find into mathematical impossibility, and it does not invent a confident answer. Look back at what made the system grow. Primitives named the domain operations. Combination connected them into trees and pipelines. Abstraction turned recurring structures into builders, macros, rules. And strategies. Interpretation gave the same data values, types, explanations, target programs, costs, and search behavior. These are not 4 chapters to memorize. They are 4 moves we kept applying under pressure. The syntax was never the central trick. Python made the first step familiar. JSON gave us a portable assembly form for a high-level abstract machine. Scheme exposed code and data. Unix exposed composition and its limits. The narrow waist was the algebraic program representation they could all illuminate. When a hard problem resists direct expression, make the meta move. Discover the right vocabulary, design how its pieces compose, build the language, and let solving the problem become the easy part to say.